what is gain in general when we talk about a system?
Gain of an amplifier. So we use an amplifier. A signal in and your signal out. The gain is the factor by which the voltage is increased.
All right, precisely. But in this case, what are the units for the amplifier's gain that they're asking us to find? Something weird, right? Not VN over V out. Our gain has units in this case.
Something
No.
Exactly.
Volts per cool.
Who knows why it's volts per pico?
You can only boost so much signal and so much voltage.
What system are we talking about in this case?
Because we're going
What's going into our preamp is units of charge, and what's coming out is voltage. So let's keep that in mind, and let's look at our system that Sam was just telling us about. So that is a capacitor, and it has a resistor. What is the function of the capacitor?
to build up the charge.
So in our preamp output, which portion of the signal is due to the capacitor?
Rise.
Exactly. Right? And so who remembers from physics the equation for voltage and capacitance?
No. QC over.
Yeah, that's something like. Yeah.
This one, right? So what's basically happening is our preamp is taking current and collecting charge, right? And so remember, if a capacitor is fully charged, it basically acts as an open switch. So in this case, this is an integrator. So it takes our current and collects it. We still want to be able to measure signal after that, and we know that there will be some maximum value that it'll reach where it saturates and we can't read anymore. So that's the purpose of this resistor. What part of the waveform does the resistor describe? Exactly. So we have this exponential decay of our resistor. How does this relate to time constants?
So like as you see, it's already starting to decay while it's still which is why it starts to decay.
Well, you could say there could be a time constant correlated with the time it takes to fall like 90% or some amount.
Exactly, that's exactly right. So this voltage that we're measuring out of our preamp is going to be governed by this equation. Right? Where this is V naught, or in this case V preamp, the square wave that went into it is V pulsar.
Section 2.2.
Okay. And so then tell me about this tau then. Do we know what tau is? Alright, so now we need to... Tau is RC. And so the time it takes for this system to exponentially decay is related to the size of the resistor and also the size of the capacitor. So that's just something to keep in mind. So the reason the hint in the class, who can tell me why the hint in the lab report said find the half maximum of this decay?
Find the half what?
The half maximum? Or maybe that's in section 2.3.
Yeah, we didn't read that.
Okay, it's coming up. So they're going to ask you to find the half maximum of this system related to this exponential decay. Who knows why?
Is it similar to like the half-life formula?
Exactly. So instead of trying to find V naught and picking random times to fit this curve, if we know this is true, and if we know we're picking this at V naught over 2, doesn't that just make this left side 1/2? And so we can measure this T 1/2, and then that could just solve us for tau. So that's something to keep in mind for the next part of the lab. So let's say what we measured so far is we know V pulsar, because that was our 5 volts we put in. We know V preamp. We measured tau from the system, but we still want to find gain. So first of all, what is V out in relation to what we've measured so far?
I mean, isn't it just the V preamp? It's the V preamp.
Preamp. Yep, that's exactly right. So let's rewrite V out. Does everybody get why? It's V preamp.
That's what, yeah, that's the
That's the charge and integrator, right? And so that is the height of that output voltage signal is how much charge it integrated. So that's the gain. So This is V preamp. Next up, how do we find the charge related to this gain? How do we find what charge went into our preamp?
We integrate it. We integrate the square. Oh, no, we don't. Or do we? Yeah, we do, right?
So there's a schematic in the lab report that tells you how to find current based on our setup. It's in the first 4 pages, I want to say.
IV over R.
Yes. And so the next schematic that we use is this. We have a resistor here, a resistor here, a resistor here, and this is our input V pulse. And we'll call this our preamp. What is our Okay. So, what type of circuit is that, first of all? Parallel. And what stays the same in a parallel circuit in each of the branches? The current or the voltage? Voltage, right? So we're saying if this is V pulsar, if I were to rewrite this circuit, it would look like this. So we're saying V pulsar is this, right? We good with that? And in the diagram, it says 1.05 mega ohms as R1.
106, but yeah, whatever.
Yep, and so if you look on your charge generator, it says 1.05 MEG. And that is just using the wrong way to dictate the fact that the resistors are mega ohms. So 1.05 MEG is telling you the resistance that we're putting our voltage through to get a current. So we put a voltage through, we put it over a resistor, so we're getting a current out. And what's the relationship between voltage, current, and resistance? V equals I. So now we're here. We have V pulsar equals the current along this branch times both of these resistors, right? But in the lab report, it says this. So we're approximating this to be the current times R1, which is this, right? So we have V pulsar, I, and R1. And so what are we going to do? What are we looking for? Grand scheme of things, why am I doing all of this?
Gain.
We are looking for gain, right? So what does gain have to do with current and these resistors and all of that?
We need to know the equivalent of V sub M.
Right? And so what's that equivalent for our preamp?
Coulombs.
Exactly. So
So we got it.
We need a charge.
Integrate current.
Exactly.
with respect to time.
So now we have a current that we're about to find, and we're looking for a charge. So if we solve for I, we get this V pulsar over this R, and that gives us a current. But we still need charge. How do we do that?
Well, you have I equals V pulsar over R1, but I equals dq dt.
Right.
So we can just integrate it,
Mm-hmm.
right? So then dq equals V pulsar over R1 dt.
Yes.
Integrate both sides. Q equals the integral of V pulsar over R1 dt.
And what do we integrate over? What does this dt turn into when you
Pulse width, yeah.
Exactly.
yeah.
Exactly. So now our Q,
And our voltage is constant, so it's not.
our Q becomes
But okay, so if we have the voltage divided by the charge, those units don't work out to volts over picocoulomb.
what are units of charge?
Oh yeah, coulomb. I was thinking of farads for a second. Yeah. it
Okay,
does,
so
yeah.
that's the next step. That's the next step.
Oh, okay.
We want, one of the questions at the end of the lab report is they're asking us to find C and R of this circuit.
Yeah.
So how will we do that?
Up to that. The last thing.
Well, Rose up. I mean, can we figure it out from the formula for the tau equals RC, and we have tau and we have R, so we have C.
We have tau, yes, which tau? I wrote two taus. I wrote T1 half here, I wrote tau pulsar here. Which tau are you talking
Well,
about?
we can solve for this tau with this because these are all, we'll find T1/2. So we this is the only unknown. So
Yes.
we know tau.
So yes, we will have this tau, right?
Yeah.
And so this tau is related through this relationship, like we said, right?
Yeah.
And so then lastly, how do we get one of those? Because we don't know,
we don't have R.
right? Because that's the R of this charge generator, right? That's the R that we put the voltage through.
Yeah.
That is not necessarily the R of the preamp.
Got it.
And so the last part has to do with gain. What is the units of capacitance?
There it is.
Cool. That's right.
Farads, right?
Multiple
So, exactly. Capacitance, unit-wise, is a farad, which is a coulomb per volt.
Right.
We deal with that? So then in that case, if we have V over a charge, is that not the inverse of capacitance?
Yeah.
So then 1 over CF is actually our gain. So we can find CF, we said we need tau, so we can find R. So that is pretty much the background for all the calculations we're doing in this lab. They tell you to find all of these things, but they never put it together in a way that's like, you start here with this circuit, you go back to this circuit, you backtrack, this is why gain is important.
Should I take a video?
Yeah. For sure. Okay.
You did. Oh, yes. That was good. That was really, that like laid it all out.
Thank you so much.
I feel good about it now. Yeah.
Cool.